Hi guys, excuse me, the end of Unit 1, 1.4, or U1A4, I guess we're going to call it Compound Events and Dependency. So I'm going to whip through this real quick. You got a little games fair thing to work on here, and then we get to what compound events are. So compound events are events that are created when combining two or more events. So something happens, then something else happens after, okay? So it could be as simple as flipping two coins. It could be as simple as firing two arrows. It could be as simple as 2 days or 9 days of weather and looking at the probabilities in that situation. So it's not one event, it's two events. And do they have anything to do with each other? Well, we'll find out. There's some do, some don't. So you want to talk about flipping a coin. What we do is we can draw a tree. So you look here. I'll just show you this one here because they've done a good job with this. If you go through it, the first coin can be heads or tails. And regardless of if the first coin is a head or a tail, the next coin can be a head or a tail. So what you do is, these are called nodes. So you start here and you say flip your coin, and then you put a branch. These are called branches. It's for a tree. And what happens is you flip a coin and then you draw the number of branches for the number of outcomes. In this case, just two outcomes, heads or tails, and head or tail here, head or tail here. Later on, we can put probabilities associated with them on the branches, but we're not going to do that now because they're equal. But you could put a half here and a half there. We'll get to that later. But in general, what you do is you follow the number of outcomes here. Each of these are equally probable. Two heads, head, tail. You follow this here. So what's going on here? You have a tail and a head to get here. So it's tail and head. First flip tail, second flip head, tail, head. Tail, tail is this one here. So you can ask questions like, what's the probability of getting two tails? It would be the number of successes, 1 over the total number of what we call these terminal branches. So they end here, 1, 2, 3, 4. 4 terminal branches. One of them gets you two tails. If you want to come up with one of each, you would go through here and say, okay, we're going to assume these are the same. Head, tail, and tail, head are the same. It would be 2 out of 4 would be the probability of that. You want to roll dice. Then things get a little messy, right? So there's 6 and 6. So now you have six branches and then 6 branches. Again, nothing is stopping you from rolling a 3 after rolling a 1 or rolling another 1 after rolling a 1. And if you want to look at the sum here, these are the sums that make up that table that we made. The fundamental counting principle here, so what goes on here is the number of branches from one node and then the other node can be multiplied to figure out the total number of terminal branches. So for example, let's just go through this again. I have 2 branches here, then 2 branches here. 2 times 2 is 4. And I have 4 terminal branches. 1, 2, 3, 4. Here I have 6 and 6, that's 36. And that is going to be the number, 6 times 6 is 36. That's the total number. If I counted all these, there are 36 outcomes. 6 from all the way from 1 to 1, 1 and 2, 1 and 3, to 6 and 1, 6 all the way to 6 and 6. So that's 36. So here we'll look at cells, for example, cells divided into 2 and then divided into 2 and divided into 2. So if I wanted to figure out how many things at the end, it'd be 2 times 2 times 2. And that's what we call the fundamental counting principle. You multiply m times n. So the number of branches in the first situation times the second situation, and you can keep going. Sometimes we refer to this as n times n, or sorry, n1 times n2 dot 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 all the way to dot. Okay. If you want to know the probability of 2 events happening, the probability of A and B happening, so these are compound events. What you do is you multiply the probability of A times the probability of B. So we'll get to that as we move forward. Independent events are events where the occurrence of one event has no effect on the other. Dependent does. Okay? So we have independent events and dependent events. In your head, you can think right now, are there things that if something happens, does that affect the chance of the next thing happening? So for example, the example I use for that, so that would be called a dependent event. It depends, the second result, depends on the first result. After the first thing happens, it's a whole new ballgame. So for example, for dependent events, I think of cards. So if you take a card out of a deck, that deck that is remaining is not the same deck as what you had. So if I was looking at the number of red cards in a deck and I pull out a red card, there are less red cards as a percent as there were before. Half the cards were red. 26 out of 52 were red in the first place. But if one's out, the remaining deck has 25 out of 51 cards that are red. So that would be an example of a dependent event. Okay. pulling balls out of we always do like balls in a hat or names in a hat. Once you take them out, if you don't put them back in, so you look for terms like without replacement, okay? Without replacement means a dependent event, right? You don't replace them. It's a new thing, okay? Independent events are things that don't matter. One thing happens, the next thing isn't affected. For example, if you flip a tail, you're not more likely to flip a tail the next time. If you roll a 3 on dice, you're not more likely to roll a 3 on the next one, or less likely, okay? So those are called independent events. Sometimes we don't know if they're independent or dependent in the world, right? And we try to figure those things out. But in general, we should be able to figure out, is there a replacement? I think of like reloading. Are you reloading the dice? Are you back to where you were in the first place? If you are, then it's called an independent event, okay? So for example, if you spin a wheel and then flip some cards, they have nothing to do with each other, right? So if I said, how many ways can you do this? It's the number of spinners, 10, or sides in the spinner, I guess, 10 and 52 cards. So 10 times 52 is 520. What's the probability of spinning a 5 and drawing a 5? Well, if there's one way of drawing a 1 out of 10 chance of spinning a 5. So let's say these were numbered 1 through 5, and there are 4 out of 52 cards are 5s. Then what you do is you multiply the probability of event 1 times the probability of event 2. So 1/10 times 4 out of 52. Put that in a calculator if you like, or use a fraction rules. 1 times 4 is 4. 10 times 52 is 520, and then figure that out, okay? The other thing you do also is not use the probabilities, but say to yourself, how many ways can I succeed by getting, how many different ways do I succeed by getting a 5 spun and a 5 drawn? And what you do here is you say, there's 1 way to succeed to get a 5 spun, 4 ways to succeed to get a 5 drawn for the cards, because there are 4 5s. And you multiply those together to say there are 4 total ways. So you go spin 5, draw this 5, spin 5, draw that 5, spin 5, draw that 5, spin 5, draw that 5. Where are the 5s? 1, 2, 3, 4. Right here. Okay. So there are 4 ways to success, and you can just use as a fraction 4 ways for success. That's your numerator. Your denominator is the total number of outcomes. There are 10. If we drew a giant tree, there would be 10 branches for the first one, and 52 branches after each of the 10. So you'd have 520 total branches. For S, so it'd be 4 divided by 520. And either way, here, if you do the probabilities, or here, if you do the ends, you get the same number. You end up with the 4 out of 520, which is just over 7.5%, 7.7%. Okay, 2 different ways to do that. If they don't have anything to do with each other, it's independent. If they do have something to do with each other and it's dependent, we have something which we call conditional probability. So conditional probability or dependent probability, once something happens, it affects the next thing. So the example they use is drawing an ace. Once you pull an ace out on the first card, there are only 3 aces left out of the 51 cards remaining. So if I was to say, what's the probability of drawing 2 aces, I could say it would be 4 out of 52 times 3 out of 51, and I could go from there. So we'll do some more examples here. We'll talk about the Denver Broncos situation. I'm not sure if this is really dependent. I'm not a fan of this question, but anyway, we'll go with it and pretend it is a dependent situation. So here, the chance of them winning on the road is dependent on if they win in the first place here. Anyway, you can go through that one here, but I'm going to do some of my own examples in a second. Okay. So here we look at these things here, and at the end you're going to have a little quiz. So let me just show you what everything looks like on a tree. So let me draw some trees for you here. Okay. So if we were to look at something, right, and I was to say how many different fours are there or something like that, and we're looking at independent events. Okay. So if I was to look at flipping a coin, we can draw put the probability on the branches here. So if I was going to go heads, tails all the way through here, sorry guys, and I was to go, what's the probability of getting a head or a tail, head or a tail, head or a tail, 1/2, 1/2, 1/2. And if I said, what's the probability of getting 2 heads, I can multiply these probabilities together, 1/2 times 1/2, or 0.5 times 0.5, and I get a quarter, okay, or 0.25. So those are independent because what you see here is these are the same things. If I was doing something like let's say I was doing cards, and let's just make it let's make life easier, okay? Let's just say I had no, we'll draw cards, but all we're gonna look at is ace or not ace. So to do that, what we're going to do is we're going to write ace, and this is the complement. We did this a few days ago, the complement of ace or not ace, okay? An ace or not ace. And I'm not putting the cards back in, okay? I'm just going to draw one card, then the other card. Okay, so I got ace and not ace. And I want to know the probability of drawing an ace. Well, there are 4 out of 52 cards. 52 cards are an ace, and 48 out of 52 are non-aces. Okay, now I'm not putting the ace back in, so now I have 51 cards remaining in each of these situations. So each of these is going to have a denominator of 51 on the bottom, okay? But the numerator is going to change here. If I draw an ace, there are no longer 4. So here I've drawn an ace, okay? So now that I've drawn an ace, there are only 3 aces left. And now that I've drawn an ace, there are 48 non-aces left. Okay, so that's how I get, see how 3 and 48 add up to the 51 on the bottom. 4 and 48 add up to the 52 on the bottom, right? Because you have success and not success, success and not success. Here, since I've drawn a non-ace, I still have 4 aces left. So 4 of the 51 are non-aces. Since I drew a non-ace, one of the 48 is gone, and that's 47 are left, which is nice because 4 and 47 is 51. So if I wanted to figure out what's the probability of drawing 2 non-aces, what I would do is multiply, this is the only guy here, terminal branch, that does that. I would multiply 48 times 50 over 52 times 47 over 51. So I'd go this times this to figure out what that is. If I wanted to know the probability of drawing 2 aces, what I could do is multiply this by this. It's the only one with 2 aces. If I didn't care about the order, I wanted 1 ace and 1 non-ace, I'd have to figure out this guy and this guy. And then at that point, you multiply this times this and this times this. And at that point, what you're going to do is add these 2 probabilities together. Okay, so if I wanted to know if both of these are success, right? If I want an ace and a non-ace, that's what I'm looking for, then I would have this guy here and this guy here, and I'd add them together. Okay, so this here is conditional probability, and this is the probability of step 2. So this would be the probability of drawing so this one here would be the probability of drawing an ace after drawing an ace. So sometimes you write that like this, drawing an ace, given that you've already drawn an ace. Okay, this one here would be the probability of drawing a non-ace after drawing an ace, given that. So you go back to, let me go back to this, no, to this, give me a second, no, where am I here? To this, that's what this says here. The probability of B occurring, after A. Okay, the probability of B occurring given that A has already happened. All right, so that would be something that would look like if we had a tree, the first thing would have an A, and then after that would have a B. Okay, so let me just anyway. So here that non-ace and then an ace. Give me a second here, guys. This isn't popping up. Give me 1 second. So if I wanted to know the probability of a non-ace, given that I drew an ace in the first situation, that would be, okay, I want a non-ace given that I drew an ace. So there's an ace. I drew an ace first, and then I want the probability that of a non-ace, okay? In this case here, if I want the probability of this happening, that's 48 out of 51, okay? Or sorry, yeah, 48 out of 51. So the probability of drawing a non-ace given an ace is 48 out of 51. If I wanted to know the probability of drawing an ace and then a non-ace, what I would then do is multiply the first probability first. So I draw the ace first. So this guy over here, sorry, my line's not straight, and I multiply it by that guy. So a little sloppy there, but what I'm doing here is the probability of an ace and then a non-ace would be this and that. Okay, so that's the given thing. Hopefully that's not too sloppy for you. Okay, so that's how that goes. There's a short quiz, very short quiz. Go over some of this stuff, and then we're done the unit. Just to review, which I'll talk about in the next video. See ya.